So welcome back, everybody, and welcome to the couple people that I know. There was the holiday down south last week, last week. So welcome people that's the first time. We covered a lot of material last week, and we went pretty fast and still went over. But we're hopeful that it's going to be a little bit more easily paced today. And basically, this is kind of going to be the formula for the rest of these classes. We're going to review what we assigned for y'all to look through in the notebooks last week. And Katie's going to cover that. And then kind of setting the stage for the main topic for today, which is really like the objective function and prior Monte Carlo. That's kind of what we're going to cover. So we drew straws, and I get to do the live coding this week. So we'll see how that goes. We're going to just kind of pick up where we left off with the demo, and then just kind of lay out the assignment for next week. So I'll turn it over to Katie to get us started.
Great. Let me share my screen really quick. So the homework last week was to go through the pest from notebook, and I could kind of briefly walk through it, but I also really want to open up the floor if anybody has any questions or any comments on the notebook. Now would be the time to have kind of a discussion around it. So Mike, if you want to kind of keep an eye on the chat, and if you want to ask a question, feel free to raise your hand, and we'll unmute you, and you can have the floor. So yeah, last week I live coded up a quite simple Freiberg pest from instance, and just trying to show that the basic pieces to get from just your set of model files to a pest plus run, a base run basically. It's not that much, but of course with any one of those components, there's quite a lot of complexity that you can be added, and a lot of pieces to think about. And so that's what the point of this class was for. We're going to be digging into each of those now. So this notebook was sort of like a fire hose edition of everything with pest plus the pest from functionality. So at the start of all these books, we're always just kind of doing some housekeeping, building our model, our template directory, bringing our model files over, making sure everything runs okay. This feels like a small thing, but the number of times I've jumped ahead to start building a pest from thing and then realize that the model itself doesn't even converge as a non-zero number. This spatial reference we had, later on in the notebook, we kind of get into this, but this is super important if you're going to be having any kind of spatial correlation in your parameters. So this basically just tells pest what the, discretization of your grid, if you want to give it your actual upper left and X and Y coordinates, any kind of grid rotation, projection, things like that. And then this is when we kind of get into the instantiating our container to start filling with all things pest. So notebook walks through that. Again, this is the most important part, was having that template directory, having, where we want what the base model files are, the template directory, whether or not we're going to replace it, that spatial reference, which is pretty important to have, whether you want to keep things zero-based, and then a start date time. This one, the start date time, is important for temporal correlation in our parameters, for example. Walk through first, bringing in all of our observations. This is just kind of inspecting those files and then adding those observations with this pest from add observations. Again, you need to specify what those index columns are, and then what columns actually hold the observations that you want pest to track. And by track, it doesn't necessarily mean that it's going to be part of that objective function. And we'll get into that some. I think the notebook later on talks about what we call secondary observations. So quantities that we want to track, whether it's for plotting or just trying to basically keep tabs on all of our model runs. You can, it's you can get up to some pretty large numbers of observations that you want to track in these ensemble methods. And it's a good thing to just, when in doubt, to add them, because it can be expensive to, run a full PEST++ IES workflow and then realize, oh, I really wish I had been tracking the like water budget components, for example, like, things like that. So definitely err on the side of add it, because it's not all that computationally expensive to do so. So yeah, any questions that you're seeing yet, Mike? Everyone's just like, I got this. Pest from easy peasy. Yeah, so the same deals with parameters. It's so clear. I think this is like the geostatistical side of it. If you haven't had a background in it, it can be a little bit intimidating. And I think, PyEmu has some really, really cool functionality for geostatistics. Various variograms models that you can use if you want, and then some really nice plotting functionalities to kind of explore it. So this is just walking through what those look like, and then we can actually start to add those parameters back here, right? And so this is walking through adding grid-based parameters for K, which is what we did in the last week's demo. Giving it our upper and lower multiplier bounds. And then these ultimate bounds are really important in the multiplier process, because often, oh, look, we have a hand up. Nice. You want to unmute?
Oh, hi. Yes, thank you. Hi, my name's Kath. I have a question about this, because I can get your example to work because it has the same number of rows and columns in the MPF text file.
Mm-hmm.
But I'm struggling with my model, which doesn't. So I get errors that say things like, where is it? Use the use calls instead. But I was wondering if you could explain how to do that when you don't have, so I have like, it's in rows of, so I think it's got 20 columns until you get to the final row, and then obviously it doesn't necessarily finish nice, I think squarely.
I think what that might be is, and Mike, you can chime in, is it using the kind of ModFlow wrapped format where it's basically your first row is actually only going, for 20 columns, and then it repeats and it wraps around and so you don't have an even number of columns throughout the full array. Is that?
Yes. So the last row isn't complete. Yeah.
That's a super common error, and actually that's a really good question. So what you'll want to do is to basically unwrap and flip all of your arrays that you're going to be adding parameters for using this array style input. You want to flip them to free format, and I can actually pull from a different code. Guys, I have to do this all the time, and I'll just like paste it in and show you guys really quick. Maybe while Josue wants to ask a question as well.
Sure. Also, kudos for saying my name right. Most people can't.
Oh.
My question was, I noticed that .zone files are made when you run that particular script, and I was just curious, what are those for? I think they're like they look like copies of the iDomain, but I wasn't sure what they're used for. And also related to the second question, how do you not set parameters for inactive cells? Like, there's a little comment, and I was trying to figure it out, ran out of time. So those are my two questions.
Yeah, great question. So the zone array is, Mike, I don't know if you wanted to jump in, but here we are using it with, this is iBound. So let's see where IB is getting set. Probably up above, but basically, yeah, we are, when we start, sorry, I just lost where I was. Everybody close your eyes while I scroll. Here, we just want to make sure that we are setting multipliers for the only active cells. And the main reason is that if you're using grid-based, right, and it is a lot of parameters that we are tracking. And so while we are kind of free of the whole limitations that GLM imposes in terms of adjustable parameters, you still don't really want to be like multiplying cells that aren't, factoring into the solution if you don't have to. So in this case, it is the I-bound that's setting it as, only putting parameters in for the active cells. But you can also use this if you have other types of zones. I, for example, have a project where we have kind of a zone of basically a higher K channel, but it's all sort of the same unit. So, I'm applying these multipliers, but I have this zone set to what that actually looks like in terms of the zone array. I don't know, Mike, if you want to have anything to add.
Yeah, no, that pretty much covers it. Like I-bound was the old ModFlow terminology, and in ModFlow 6, it's I-domain. And if you're using a different model that's not ModFlow, right now the logic is if the value of that grid is either 0 or negative, it's considered an inactive cell, and no parameters will be assigned there. Another quick thing with the zones is if you have other integer values in there, each unique integer value can be treated as a zone for pilot points, or for grid. Well, for pilot points, interpolation will only happen within zones, so you can kind of segregate some lithology that way. And I think that then the zone file you're asking about that gets printed out is just the result of sort of how this got interpreted, just so that you can kind of confirm that.
Nice. And so to go back to the previous question, this happens all the time, especially if you're working with older ModFlow models. Like, for example, I'm working with a ModFlow 2000 model right now, which is just, it hurts me to say that out loud. But so I have to do this all the time because it, the old school style was to do this wrapped format, which is like, I think it's like came from the Fortran days. And now with ModFlow 6, everything can be free format, which is super nice. But I think, a lot of people are still working with like Newt models or older, and so they will be often wrapped. And so this is just one, and I can paste this in the chat, but basically I have a step before I go through adding parameters to read in all of those array files. And then just, it's just using some, this like pandas read fixed with format and some funkiness to try to basically reshape it into what our free format array is, just by rows and columns. And that is what PEST, or what PyEmu expects when it's adding grid style parameters. So that's a really good question, and I'm glad you pointed that out. Yeah. And I think that it should still be fine. I don't know what model version are you using?
Yeah, so I'm using ModFlow 6 with a grid, so through FlowPy. So maybe it's just that I'm not setting I've set all data external, but maybe there's some options there that I need to check.
Yeah, that is interesting. It usually does. Mike, do you know of any arguments that could be?
Yeah, I actually thought it's only, you could maybe make it wrap in FlowPy, but by default it doesn't. So that's a little surprising, that you're getting that issue. But yeah, I think, but typically this is the reason, and this is a good solution.
Okay. Yeah, so this is just saving the out file and giving it this specified format, whatever. And I'll paste this in the chat for everybody. It's just one, like, there's a lot of different ways you can do it. This is a hack that I have found works. But yeah, that's a great question. So yeah, we just walked through adding the grid base and pilot point. And Mike, if I'm going way over in time, I think I probably have already, but this is probably good to go over.
No, it's important though.
Yeah.
We just might go slightly longer again.
Yeah. Yeah, we're just going through, and this is a nice function that somebody wrote for probably Jeremy or Briak on adding multiplier parameters, but wrapping it in a function, which is generally really nice to do in these workflows if you know you're going to be having to do this over and over again, to just like wrap it once and give it those bounds basically are all you really need if you know that you want to have the kind of multi-scale multiplier approach here of grid to pilot to constant, for example. this is that some examples we walk through of adding in that temporal correlation here, which is important for these, something like recharge or any kind of time varying specified flux, for example, or and then yeah, an example of how to add parameters for something that is in a list file format. So a GHB, a lot of the boundary conditions are list based, unless if it's like recharge or evapotranspiration, those can be array format. And yeah, just kind of walking through all of that. And I think I probably, and then this was the important one that I left out in my little live coding effort, was we actually do need to have that forward run script, that we have that forward run command is the most important part, but then you can add in pre and post processing functions. So this is an example of adding in, that's that model run command there, which is a list, right? So we can append many, many things to this list. And you can also, when you append that, to specify whether you want it to happen before or after that run call, which is important if it's a pre or a post processor, for example. So here's an example of that add pi function where we want to have it run after the model run, so that this is pre-CMD is a important thing that you do want to make sure you're setting correctly if you want it to happen in the right order in your script. So we're basically have this function that exists in this Python script, and we're saying we want to add that to our forward run script as part of ours. And this is a bit about those secondary observations that I already talked about, that we want to err on the side of adding them if you think that, you might need them for any number of reasons. And I think I will end it there. Oh, we talk about adding forecasts to it, but I think, and then we just run. Yeah. But basically, I wanted to, what we've done here is we've wrapped that Freiberg model using pest from. So we've wrapped it. Nothing has been intrusively edited, right? So it's all just keeping those original model files and then operating on them with these multipliers and operating on them with these instruction files to grab the simulated outputs that we want for our pest run, right? But we haven't messed with anything beyond that to influence the objective function. So that would be, messing with our weights and our noise, which Mike is going to talk about in detail today. And we also haven't evaluated that prior yet, which I'm going to talk about after Mike, through a prior Monte Carlo. And just to kind of remind everybody of the theoretical underpinnings or statistical underpinnings of this is it's a Bayesian rather than frequentist approach, where we're talking about distributions of parameters and observations for our prior, and then a distribution of our data, basically our likelihood here, and then our distribution of the posterior, what we're getting to. So what we're focusing on today is this likelihood function, which is the objective function in Pestland, and then this prior here. And I think Mike wanted to chime in and talk about kind of one of the more important parts of this.
Yeah, I mean, so one of the cool things about this Bayesian framework is that we're acknowledging that everything is conditional. And really what that means is when you look at the posterior distribution, which is it's both the estimated parameters from this process, but it's also the model outputs from this process. You could look at it either way. But really when we're focused on these parameter sets, they are conditional on both what our prior was and what we learned from the model. And the way that I like to think about that is if any of those things change, the answer changes. And this used to be, I think this is one of the reasons that kind of the word calibration has fallen out of favor a bit, because calibration kind of implies this single answer that, that has been derived, that's like very exact and that is correct under all circumstances. And what we're acknowledging here is information from the prior, like what we start with and what we understand at the beginning of the modeling process, and what we learn from the model both contribute to where we end up. And we end up in this kind of big loop where we reevaluate the prior from time to time, and we reevaluate the behavior of the model. The behavior of the model can be reevaluated by changing the model, like changing a process, how something is represented, or the grid, or all kinds of, or even the code itself, all kinds of different things like that. And also how how information from the model gets put into this process, and that's what we'll be talking about with the objective function and weights and stuff. So, but this idea that it's conditional, I think, is just really important to bring home, because we're really bringing in some transparency here. When we say that we have a set of parameters and then, you know, forecasts that are made from those parameters in that model, we're just acknowledging all the things that it's conditional on, so that if people take issue with, you know, if you want to have an argument about whether these are good outcomes, we can look at the whole process, not just, well, we put it in a block box and this is what we got.
That's great. Yeah. All right. I'll dish it back to you then for going through obs and weights to dig more into that likelihood.
Cool. Let's see. Let me make sure that I'm getting the right. All right. Just trying to share one notebook here. So this is basically the live coding demo that Katie went through last week, and I'm just going to basically run it. I made a couple little changes. This is actually in that cheesy kind of fake repo that we made, reimagined adventure, I think. So maybe we'll actually share this if people want to mess around. But so the only real difference that I made is when we added the parameters, I'm sorry, when we added observations, actually added several locations at the same time. And so the idea here is we have time series at a bunch of different locations. And when we ran a single run, so remember there's this nopt max value or a parameter for pest that allows you to run the model through pest just once. And when we did that, we got an objective function of 0. Seems too good to be true, which it is. But the reason that we do this is it's a great diagnostic, because what we used as quote unquote like field observations were actually the same as the model outputs at the initial parameter values. So the residuals of all those should be 0. That's great. But so the first thing we really need to do is bring in actual observations. And so what I'm going to do here is we've got this pest control file object here, and we can update it by bringing in new observations, the actual observation values, and then take a look at how we construct our objective function. And so this is a little bit cheesy, but I found we have this is a monthly model, but it's based on a daily model. So I'm just going to say, you know, like true obs is, we'll just use pandas to read in a file, and it's in data called obs true. All right, and we can take a look at this thing. If we are consistent, live coding. So this has time series again at much finer resolution than the actual times that are in that we are outputting from the model. So we have, I think, the observations, we have 325 times spread across several places, but this thing is much longer. It's like, oops. Oh, I already lined it up. Never mind, just kidding. I already did we didn't want to go through this horribleness of there's a lot of pandas shenanigans to line up the data to the times that you want. And in the notebooks that you're going to be looking at for your homework next week, it'll go through that in a little more detail. There are important choices to make here. But what we can do is pull out, we talked a little bit about this last week, that once we're in PyEMU, the observation section of the pest control file is represented as a pandas data frame, which is really handy for doing things like making changes to values. And so one of the columns is the obs val. And I will say I've run into a little bit of confusion. We use the term observation when we're talking about pest in kind of two ways. It means both modeled outputs and field observations. They tend to get like used interchangeably. So I try to say modeled outputs or something like that and field observations, but forgive me if I trip up. But observation values here means actually what was observed? What are we trying to match with the outputs from the model? And so I'm actually just going to cut and paste a little piece of code that I did the other day, because this is strictly pandas, but I just want to show you one way that we can actually line this all up. So if we loop through this observation data, we've got a little bit of metadata that PyEmu is pretty slick about pulling out of these names. As long as if they're named in pest from, some of this metadata is pretty accessible by PyEmu. One thing is which column are we using, but really what that means is sort of like a base location. This is like one well. It's being sampled at different times, and then this is the time. So our true observations, we'll look back at this really quick. True obs basically has a location column and a time column, and then an observed value. And if we look at this first one, this happens to be this value, we can see it's not the same. So this is like what actually came out of, supposedly was measured in the field, and it's not the same as what we get out of the model at the beginning of our process. And so just doing a little bit of pandas trickery, we can, we can basically loop through, like look at each observation location and just find where the time and the location match that true obs, pull the value out, and stick it into this obs val location. So strictly a pandas job there. So, but then now we can see we replaced. So this value, this very first one was 34 or something. We can see that we've replaced it with 35 something. So it wasn't that far off. But now we have a set of real observations. And you'll see this in the notebook that you're going to go through. And you'll also see this, and this is something you always end up having to do. So the diagnostic step of having, the quote unquote observations be commensurate with model outputs is this great diagnostic, but then we need to replace that with real field values. And so there we go, we've got that done. And you'll notice that the weights are all 1.0, that's the default. And so remember, we're making an objective function. Well, maybe not remember, we didn't maybe talk about this quite enough, but we're basically the objective function that pest++ in all of its forms is really going to be trying to solve. It's trying to minimize the sum of squared residuals. So for every well and time, or every location and time, there's a discrete number, like one of these, of what comes out of the model and what's observed in the field. And we take the difference of those, square it, divide it by, or multiply it by a weight, and then sum all those up. And pest++ is trying to minimize that quantity. So the weights play a really important role, several really important roles, but part of it is basically making up the different components of that objective function. And what this means in practice is, as the pest++ algorithms are trying to minimize that function, if there are quantities that make up a lot of that function, then the algorithm pretty quickly determines that reducing those misfits in those particular areas will reduce the function itself a lot. So an extreme case of this could be if you start out with, say, 10 head values in a groundwater model, and they're all in the order of like 100 meters, above sea level. And then you've got some kind of flow metric that's in, maybe that's in cubic meters per day or something, some unit like that. Those numbers may be much, much higher. And if you only have one value of flux, but you have and 10 values of head, but that flux value is so high, the objective function will be completely dominated by the misfit of the flux, and that you'll get great improvements of the objective function by fixing the flux, but the heads may be way off. Or the other could be true. You only have one flux measurement, and maybe it's in units that are pretty small, and you have, it's not uncommon to have a few thousand head measurements over time and space, and that will dominate, but you might get the water balance totally wrong. So trying to link this all up is really important. And so 1.0 is probably not an appropriate weight. So, but a good way to start this out is to start with your weights of something that you feel like is supported by, would you be able to defend that level of fit? And that sounds kind of squishy and subjective, and that's because it 100% is. Like any discrepancy between your modeled output and your field observation is a function of the model being not perfect, the observations being not perfect, the parameters in the model being imperfect, all these things. So really what it ends up coming down to is, what could I defend? What could I say, yeah, we got this fit within a certain amount, and that's sort of reasonable. We could talk for hours about what that really means. But so for example, if these are all head values, maybe I would just say, I think within, you know, half a meter would be sort of defensible for each of those. And so now if we look at this, we've just reset this whole column to be 0.5. In reality, you'd probably have some differentiation in here. All right, cool. Oops, and I forgot I needed to do something else first. So rather than using this PST object that came from here, there's a nice way in PyMU to read in an actual pest control file. So we can just read in the Freiberg.pest. Oops. We'll try an equal sign. All right, so we can just run through these again. All right, so one of the things when PyEmu reads in a pest control file, it also tries to find whether there's any information about residuals from an existing run. And this actually now has that information. And there's some nice shortcut functions for plotting, and one of them is called the phi plot. So if we look at this, this is dynamically calculating what are the residuals of every, in this case, every head location, given the weights that we've assigned, given the observed values that we have, and whatever the single set of model outputs are for the basically the initial run, the run that we made with our starting parameters. And so right away, we can see that this is not super balanced. There are three components of this objective function that are quite a bit higher. And for example, this one is really low. In this case, these are all heads, but what if it was, you know, heads versus fluxes versus concentrations? This could be a real problem. And so one of the first things that we often do is rebalance this. And in this case, I'm just going to show a way that you can give them all equal weight. Probably you'd want to be a little more sophisticated. But so we can just say like 1 over the number of observation groups, obs groups, times the initial objective function for each of these, for each group. Groups. All right, so now what this is showing us is it's going to assign for every group that we have here, it's going to assign the same value. It's basically subdividing the objective function into equal components for each of these. And then there's this great adjust weights function that takes a dictionary like this. So for every group, you just need to have the name of the group and what you want that objective function component to be. So obs group dict is the dictionary that we need to give it, and we can give it new balance because we like sneakers. And now if we say pest dot plot again, this pie chart, oops, and we learn how to type. Now this is great, right? So we've there are utilities to do this, and this has been around in Pest for quite a while. But again, this is maybe a place to start, but I would say like 10 times out of 9, I end up wanting to like fine tune this a little bit. And again, this is where some subjectivity can come in. You can also have groups that have all 0 weight. Some of the diagnostic or auxiliary observations that Katie mentioned earlier can be useful for that. And let's just take a quick look at what this did to our observation data, to our weights. So now the weights are variable by group. So one of these is 0.83, one of these is 1.0, right? So it made these adjustments so that from the start of our parameter estimation process, which we'll get to next week, everything is equally playing an equal role in the objective function. Then the only thing that will change these, if we hold the weights the same, the only thing that will start to redistribute this is where the model is fitting better or worse. That's kind of how that's going to behave. So this is a really good start to get us to basically starting the prior Monte Carlo, and that's what so the lessons for next week and what Katie's going to talk a little bit more about now are getting this getting this all set up and running a prior Monte Carlo. And I just want to demonstrate quickly how that's actually pretty straightforward to do. That NoptMax parameter, you'll see in the notebooks, there's another tool called Pest Sweep or PestPP SWP, which is very powerful because that allows you to sweep parameter values for a whole range of parameters, but it requires a little bit of extra setup. And the value of this prior Monte Carlo step, once we get into the iterative ensemble smoother, this step is so important that that now there's actually a control data NoptMax setting of -1 that will just run the prior Monte Carlo and stop. And yeah, I don't think we'll be able to stress enough how common how much time it makes sense to spend in this prior Monte Carlo loop. There's one other thing that we need to set. If we look at the parameter data, again, we were using multipliers for the grid parameters. That's what Katie set up last week. So there's 800 of these, which is cool. And their initial parameter value is 1.0, which is also cool. But the lower and upper bounds are like 10 to the -10 and 10 to the 10, which this just means that they're basically not playing a role. And in the parameter estimation process, typically, the bounds were only like a backstop to keep parameters from going to extreme values. But in the prior Monte Carlo, the Pest++ will interpret these bounds, unless you do other things. By default, it'll interpret these bounds as like the edges of, or like plus and minus 2 standard deviations of a normal distribution. And to do the Monte Carlo, it's going to sample a normal distribution in that range. If we use this range, we would have significant number of values that are greater than like 10 to the 8, right? Which is clearly not going to be correct. So it's very quick we can just set all of these because they're multipliers. We can just say pst.parameter data .par lbnd. So we're just going to set all the values in this column to be, say, 0.5. And we can copy and paste this and do the same for the upper bound. Take a look at what this does. Cool. So it just, oops, I didn't want that to be 0.5. Let's make it 1.5. All right. So now we've got, I mean, and this may or may not be the appropriate parameter range, but at least this will give us something somewhat reasonable. And so if we just write this out to the template directory, and maybe we could call this like Freiberg Fryer.pst. It's now written out all of the files that we need to actually run this. And I'm having some path issues on my computer, so I'm just going to smack this and pretend it didn't happen. And then Mileage can vary. And then there's this really great function that is called start workers. And this, you're going to see this in the notebooks. And I don't think you've seen it yet because it's only for running in parallel. And there are some pretty important ramifications of this later. And I would say in kind of quote unquote real work, this is generally not the way that we do kind of production runs, because but it's great for these kind of demonstrations. And what this will do is it'll take the template directory, or you can tell it which directory contains all of the model files and pest files that we want to run. And then we can assign a new master directory. We'll call this like CM prior. So what pest is going to do, this utility is going to do, is make a copy of this here in this master directory, and then all of the results will be written into there. It will then spawn a number of workers and run them in parallel, then delete the directories for us to clean up. So there's just a few other things that you need to supply this to get it to work. The executable relative path, what are we actually running? This is going to be pest++.-ies. And then the pest relative path is what is the name of the control file that we're going to run. It's going to be the one we just wrote. So Freiberg fire.pst. The worker root, this just means that when it gets to the worker directory, it's running in the actual directory that we think it is, not a subdirectory. And then num workers, this is pretty important. This is how many parallel, both copies of the directory it's going to make and how many runs it's going to do concurrently. This does not need to equal the number of processors you have on your machine. It can actually be more. There's some hyper-threading, but the higher you go, the more your fan spins and your laptop wants to melt, and maybe things just stop working. So, you might have to experiment with this a little bit, and you'll see that this is called out in the notebooks that you're going to be running. But when we start running this, we get a nice dialog here. This is actually running pest++ now. And we can see how many agents or workers are running. We have 10 running, and then we'll get a tally of how many runs have completed. I did not set the number of realizations that I wanted, so it defaulted at 50. So this is actually going to happen pretty quickly. All right. And then now let's notice that we don't have zeros for all the components of the objective function. We have something a little bit different. The mean value is pretty close to what we specified as our desired start. But there's some variability because we've run the model 50 times, sampling the inputs 50 different times and getting different outputs. So that's what we get here. And then processing this and actually going through what this starts to mean is going to be the subject of the notebooks that you look at later. So yeah, so I'm just going to talk about one other aspect of the weighting that's important. And then I will turn it back to Katie to talk about the prior Monte Carlo.
Do we want to pause here and see if anybody has any questions?
For sure, that's a great idea. Yeah, feel free to raise your hand and we'll, oops, I see someone's in the chat. Oh, that's your.
I just added some code, yeah.
Awesome.
Yeah, I think the pest algorithm is very opportunistic. So this weights thing, it just wants to chase where it's going to get the best bang for its buck. So you have to, it's not very smart in that way. And one thing that I always do, because I add a lot of those secondary observations, is just right off the bat, set everything to 0. That way, you're not adding in observations that shouldn't be factoring into the objective function. So set everything to 0 and then go through that process of looking up the actual measured value and the weight that you want to give it.
Yeah, absolutely. That's key. And now, like resetting the weights and rerunning the algorithm is actually a loop that don't think that you're going to set these weights once and be done. In fact, I found that in most projects that I work on, I spend more time in, sort of reevaluating the objective function and rerunning the entire optimization than I do setting it up or, writing the report. So,
Yeah.
All right, cool. So one interesting thing, and as we've both said, and hopefully this is sinking in, like how you weight components of the objective function, that controls this opportunism of the PEST algorithm. It's going to go after the biggest components. That's just sort of how these algorithms behave. And so, but now that we're in this kind of ensemble world, we can actually sample noise around the observations as well. And there's a default behavior of this, which works pretty well. But there's also a way to control it that I just want to show a little bit, because this is going to come up again later. But so just like imagine we just have one observation and we run the Monte Carlo and we get a distribution of modeled output. So that makes a histogram here. And then this orange line is the observed value. So ideally, we would want to kind of center this distribution on the observed value. That would be something that we are happy with. If we totally miss this is going to be a problem. This is something called prior data conflict that we're going to come back to a little bit later. So initially, we're just trying to evaluate whether we're likely to be able to hit our data. It's going to be, does this histogram intersect with this single line? But in reality, we can actually sample these values. And so what we're really looking for is overlap. Like so we can actually sample the noise around the observations as well as we sample the noise by running the model in an ensemble way. We're sampling noise around the parameters. And so, the prior data conflict would not mean that this observation or that the model outputs don't intersect the single line. It means that whether these two distributions actually overlap. And by default, PEST++ will use the reciprocal of the weights as a standard deviation to make this sample. And as I showed before, like initially, we set our weights to be sort of the reciprocal of the standard deviation. Like what do we think would be reasonable? But once we start to rebalance the objective function, that can get out of whack, and we can end up with something like this. So the orange distribution is the noise, the uncertainty that we think is appropriate for those observations, and the model hasn't changed here. But if we redistribute the weights, like I showed, just kind of rebalancing the objective function, we might end up with weights that either shrink this to be like no noise, or make the noise observation seem like they're really big. And this has really important ramifications for the algorithm. So basically, the bottom line here is that initially, observation weights and the uncertainty around the observations is very closely tied, but we have a way to decouple those two things when we're using ensembles. We're going to talk more about it, but I just kind of wanted to show this behavior really quickly. So cool. I'm going to pass it back to Katie then to start talking about the prior Monte Carlo.
Sweet. And just a note on noise. It can be, anything as like concrete as measurement error. So like, there's some error for every water level measurement that can impart some uncertainty in what that observed value should actually be or could be. But more often it's dominated by signal components that are affecting that, real world quantity that are not in your model. So, say you have daily data, but your model is monthly stress period, right? There's going to be components in that data that your model simply is not representing because we're not allowing stuff to, vary on a daily or even sub-daily time scale. So that's, there's always going to be noise. That's my little soapbox. I'm going to get off of it now. Let me share my screen. So, these are notes. Yeah, so Mike walked us through what we're the start of what we're going to call a prior Monte Carlo. And yeah, both of us, like, we really cannot stress enough how powerful this, this exercise is for any modeling project. And it doesn't take much to be able to get to the point to run a prior Monte Carlo. You just need your parameters and the bounds set in them. And you need your, observations that are weighted and, anything else that you want to be tracking. But mostly it's the weighted ones that we do care about. And those weights aren't going to be factoring into any sort of upgrade or history matching yet, because we're just evaluating that prior parameter ensemble and then basically qualitatively looking at it compared to the observed data. And so this is the prior Monte Carlo, Freiberg prior Monte Carlo notebook that I'm just going to walk us through. But, it's got the same housekeeping stuff here that we need to do before we start all of this. We're just going to load that model, load that path in that Mike was showing, that cool thing where we can just load it directly from the pest control file. Just make sure a certain notebook has run. And then, yeah, we're going to run it in parallel, which is what Mike thankfully was talking about. This is going to be showing how you do this with Pest Sweep. But yeah, like Mike was saying, you don't need to necessarily use Pest Sweep. You can just set the nopt max to -1, and you have, you're telling Pest to evaluate that prior ensemble. But Pest Sweep is nice because it kind of records everything in one place. So you get a nice CSV output file that says, here's all of the realizations in by rows. Here's the ones that failed. Here's the fee for all of them. Here's those observed values. So it does print things out in a nice kind of contained space, if that's what you prefer. An important thing that I don't know, Mike may have touched on it or not, but if you don't specify a prior ensemble, parameter ensemble, Pest++ is going to assume one. Basically, it's going to draw one on its own, assuming those bounds that you give it in the control file. So if you want to give Pest more detail in terms of covariances or, like these geostatistical correlations that we have, there is in the Pest from notebook that y'all did for homework, this PF draw function that you can do prior to running this, right? And so this is what this notebook is assuming that has already been run, and then this is that parameter ensemble in a compressed binary format that's already been built from the previous notebook. But that's what that important step is. But you don't necessarily have to give it that, but just know that behind the scenes, Pest is still drawing a prior ensemble. And when we talk about drawing a prior ensemble, it's essentially, using Monte Carlo, sampling randomly within your distribution. So if you think back to that Bayes, Gaussian distribution, we're basically sampling it at random, which are going to be, when you sample it enough at random, you're basically, it's that central, it's the central tendency theorem, or the law of big numbers, that if you sample it enough, you reach a sort of converged, prior distribution, right? So when you're running a prior Monte Carlo, you want to make sure that you have enough realizations that you feel like you are exploring that prior parameter space. So that's something to keep in mind. And of course, every model has, and every project has computational limits. So it's often, a little bit intense to run like 1,000 realizations, for example, for a prior Monte Carlo. But you definitely want to get into the couple hundreds. And it's a good idea too to kind of test a couple different sets of number of realizations, just to make sure that, you are making sure that you're sampling that fully, and you're not, that's one to think about if you see a lot of prior data complex, for example, is just make sure you double check that you've got more than, say, 50 realizations, which is what Mike was running, because it just, in that case, could be that you're just missing it because you didn't give it enough chances to explore that space. So yeah, here we are running Pest++ sweep. And so this is just, when you want to run it in sweep mode, you have to give it this control file argument right here, which we're basically saying, here's that prior parameter ensemble. And then because we're using sweep, this nopt max is not -1. It's ignored because we are going to sweep through it and do a prior Monte Carlo here. So we write that in that compressed format here. We do a little test run first, make sure it runs okay. Calling that, running it, and it's little compressed. Okay, cool. We're in good hands right here. So we have that base run that went well. So here's that that parallel local number of workers basically that Mike was talking about. So this is just a nice little command that automatically detects how many cores your computer has. So if you don't want to think about it, you can just put this, or if it's a code that's going to be shared across lots of different laptops with different configurations, this is a good one to do. I think mine has 8. And I generally just go with the 1 per 1. A lot of the times your limitations end up being memory more than actual processing power, because PEST can be a bit of a memory hog. So that's another thing to think about. And so setting that master directory here, and then running that start workers command. So we have the master directory, we've given it the template directory. We're saying we want to use PEST plus sweep, but it's IES basically, but sweeping through your parameter ensemble. The control file, number of workers that we've detected from that command above, and then we want to run it. It's going to take a little minute because it's going to run 250 times. But while we wait for that to finish, so the main thing we're looking for are what Mike was showing is this thing called prior data conflict, which is basically once you feel like you have, a prior bounds for your parameters that are sufficiently wide, right? You want to start with a pretty conservative stance on uncertainty, and with a sufficient number of realizations that that you're sampling that prior appropriately. Then, if you have instances where your observations are still falling outside of, even with that observation noise added, still falling outside of your prior ensemble outputs, right? And that outside term can be subjective, right? There can be some overlap maybe with that observation noise with your prior, but in general, what you want to see is that the observation plus noise is being basically fully contained in plot form by your prior ensemble output. And if you have a lot of prior data conflict, which PEST++ very conveniently records for you in a CSV, I think it's just whatever your PEST control file name is, .pdc. It records all of the instances of prior data conflict. So for every single location and time that is in conflict with your prior ensemble, you have that output pretty conveniently. But there's a number of things that you can do once you have that happening, maybe more than half the time or something. And we'll kind of talk about that in just a second. So we've gone up to 48 slowly. I guess I can just start into it. So the first thing that you can do, and this is not in any kind of order of preference, it's just these are your options in that case. You can always inflate your prior, right? So maybe you have a lot of prior data conflict and you realize that, oh, I was probably being too conservative on my recharge multiplier. And this is, again, something that you have to think about defensibility, because you can inflate that prior as much as you want, but if you have to go back and say K ranges from 10 to the minus 10 to 10 to the plus 10, then, you're going to have a bad time. But the other thing to consider is that the more wide your priors are, the more extreme values that PEST is going to be exploring. And so often what you'll see when you're exploring those kind of more extreme values is that you get a lot of non-convergences in model instability. So inflating the prior helps, but there's some downsides if you inflate that too wide. The other one is to take another look at your observation noise, for example. That is something that I can say that I often forget to spend a lot of time on. And it's this, I would say it's, almost on the same level of importance as weights, but not quite. But that's one thing that could be happening. Maybe your observations are actually noisier than you first anticipated. And then the kind of more squishy, but a really important thing that you can do is revisit your conceptual model, or revisit the sort of the structure of your model. Oftentimes, you have conflict in places where it's, again, happening due to this really like local scale, kind of fine scale process that's impacting that observation, that is just simply not in your model, right? And then that brings you at sort of this crossroads of, okay, well, I can go back and add some complexity to my model, or redo the discretization. Maybe I'm missing some important, boundary condition. But then there's also the other side of that crossroads is, what is actually important for what we're ultimately using these models for most of the time, which is some sort of prediction, right? So say, there's this local process that's leading to prior data conflict at this one well that, you just realize it just doesn't have very much bearing on your prediction. There is an option in PEST++ to basically drop any conflicted observations. So basically what that does is it doesn't, you zero weight those, and they don't factor into that objective function. And it's basically acknowledging that, the model is not going to be a perfect representation of reality and all of the complexity that comes with it. And so, we are going to not try to match, and we're not going to, based on the conditional thing that Mike was talking about, conditionally, we know that the model is not at this, appropriate representation to match whatever that observation is. And so we don't expect it to match it. And I think am I missing any other prior data conflict?
I mean, I would just add that that option is a little tricky because, sometimes when you first run your first Monte Carlo, like you can have tons of prior data conflict because of something really systematic in the model. And so I think it's always worthwhile to review those values as well. You can set it to just ignore them and keep going, maybe in an early phase. But I would say, like, I spend a lot of time looking through and maybe working with other people who know the data better sometimes to see which of these multiple things that Katie mentioned are at play here. Is it a problem with the observation? And if it is, cool, then giving it 0 weight definitely makes sense. But if it's a defect in the model or the parameter values, there may be something that we can do to improve that situation rather than just ignoring those data. So it's a helpful diagnostic as to defects in the underlying process. So I'd say it makes kind of a loop, but yeah, it's a super valuable thing. And back to the law of large numbers, like assuming that we had a full representation of the parameter distributions, that should be giving us, in theory, a complete representation of the modeled output distributions. And if those don't overlap, then running parameter estimation is not going to improve that situation. If we have completely adequately sampled valid parameter space and we can't fit those observations, parameter estimation isn't going to do it. So it's just a very important metric.
Perfect. That got us right at 250. Nice. Now we can look at this, and everybody with bated breath is wondering if we have any prior data conflict with this. So first thing, with this sweep out.csv file, and I'm going to try to locate that file live, prior Monte Carlo. And again, if anybody has any questions, jump in. The prior Monte Carlo thing is super important, but this is that CSV that it generates that I find. Oh, it's quite a large one, but we'll load it anyways. So we've got our run ID, the failed flag. We've got fee and measured fee, which is the measured fee is the one without noise, Mike, and then I forget. I always get these mixed up. You basically it'll give you the fee when you have noise and when you don't. And by noise here, we're talking about for every realization that you have, a drawn realization of parameter values, PEST is also drawing a realization of observation values. So that's where that there's the original value, and then there's some kind of increment that it's adding to it from that distribution of noise that you've given it. So that's what that means for every single realization. And then you have, for all of the observations that we are weighting, we have values here. And notice that we don't have any observations for the ones that we aren't weighting in this sweep that out. So let's go ahead and nicely here, we don't have anything failing, which honestly rarely happens in the real world, but this is the Freiberg land. And let's plot that feed distribution here. So we have, a distribution, although it seems pretty centered around, well, I guess this is a huge axis. It's hard to see. I would need to kind of, I'm not going to say anything about this 1e to the 6 in log space. But let's go to our one-to-one plots by these observation groups. So this is one way you could look at prior data conflict, as these nice one-to-one plots. And I think one of the things that, Mike was making a good point about is that you do want to kind of expect these like group by group and sometimes location by location, because, something like, are the residuals correlated, is like a nice indicator that maybe there's something here that, is a process, for example, that is imparting some signal that I am missing. That would look like a correlation in your residuals. Right. But what we're seeing here is these ensembles, which is plotted, as these kind of vertical lines. So for every single observed value, this is our, ensemble of outputs. They are containing that one-to-one line is what we want to see for these types of plots. There's another way that probably people are more, looking at it with noise now. And you can't really see it because the noise is pretty small for heads. But when we get down to, say, stream flow fluxes, you can see that's that noise distribution around our observations. And again, what we want to see is that our simulated equivalents are, the prior is containing that, those noise realizations. Another way, again, and these are all really handy plots that honestly just is like nice to copy and paste into any kind of workflow that we're doing. It's just look at it in those one-to-one plots, look at it in these histograms. Histogram is nice because you can actually see, is the red falling within the gray is essentially the diagnostic that we're looking at. And fortunately or unfortunately for our class, we don't have any prior data conflict happening in this case. So in this case, well done, everyone. You can move forward if you want to start doing some history matching and parameter upgrade to try to contain it. But often, in many projects, and I know Mike is a proponent of this, often a prior is enough, right? If you are moving towards some sort of maybe management optimization, all you're trying to do is get on the dance floor, right? To say that your model is appropriately representing the observations that matter to the degree that they matter. And now, you want to move forward with some sort of conservative estimate of uncertainty that is defensible in terms of your parameter bounds, and try to, do some sort of management optimization around that. So, it's a powerful tool for diagnostics, and it's also a powerful tool in its own right. You can do quite a lot moving forward, even just with this your prior ensemble of simulated results and parameters. So yeah, this is that observed versus simulated in the nice time series fashion. And what this would look like if you had prior data conflict is, red dots occurring outside of this sort of spread of our prior simulated equivalents. So I think that's probably all we really wanted to cover today. Is there anything else I'm missing, Mike?
No, I don't think so. Yeah, this is so there's a set obs, vals, and weights notebook in part 2, and then there's this prior Monte Carlo notebook in part 2, and that's so digging in and maybe doing some experimenting with that is really what we're asking for you to do for next week. There was a question about variograms in the chat that I answered there too, if anybody's interested. And we can always talk more about that if there are further questions in the future. And just again, the parallelization, now that we're running prior Monte or any kind of Monte Carlo and moving into the iterative ensemble smoother, this parallel running is going to be really important. And so just again to stress, like that number of workers parameter is going to be is something to keep your eye on. If you're running on an older or not super strong machine, you know, you might want to scale that back a little bit and go make a cup of coffee while it's running in parallel. And for full scale large projects, you know, we end up, that tool isn't usually what we go to. There are some others, and again, that's something that we could kind of point to resources for if people are interested in the future. Oh yeah, so I guess that's it. Was there anything else you wanted to add, Katie?
I think that is it. Yeah. No other questions?
And yeah, one other thing sorry, go ahead. I got to bring up, so I work for the federal government in the US for the US Geological Survey, and we have this semi-annual tradition of Congress not funding the government and kind of closing things every once in a while. And that looks like it might happen next week. So if that does, I won't be able to participate in the class. So we're working out whether we would postpone or possibly somebody who does not have that restriction would take my place. So stay tuned. We'll keep in touch via email. I mean, for now, we'll just plan on it, class as normal next week, but I may or may not be able to join. So, which bums me out. This is fun.
Yeah. And just as a reminder, we're going to say this every single time, the GitHub discussions for GMDSI notebooks are, a really good place to, if you have any questions that come up in the meantime, or even during class. I think I'm probably going to go ahead and add that one question about the wrapped format, because I think it's a really common one and a really good question that maybe we can just add for for everyone to benefit from. But
yeah, I would second that for sure. There was maybe some people saw there was a little bit of discussion about something about like Linux and Windows, like really deep in the nerdy weeds, but like those are interesting things and real questions that people have. So yeah, even the questions that were asked here in the chat, if people want to put those into the discussions, even if we answered it, it's just another way that hopefully our community can continue to grow, and people will be able to find these things just by Googling around. It can be hard to answer some of these questions. So yeah, think about that.
Great. All right. Thanks, y'all.
All right. Thanks, everyone. Hopefully see you next
week. Yeah.